Okay, so I've got a half a kilogram collar freely on a smooth rod, so there's no friction on AB. Uh, at a given instant, A is rotating, angular velocity given, angular acceleration given. It wants me to find the normal force of the rod and the radial reaction at the end plate. Okay, neglect the mass. Okay, so let's just draw a free body diagram. We'll draw it right below here. And again, I'll just treat the collar like this. It will have a force straight down. That is the 0.5 times 9.8. That's just the weight of this guy. I'll also have a normal force pushing straight up, but I'll call that F in the Z direction. And we're going to set this up in polar coordinates since it's giving me theta and theta dot. Okay. And I know my radius out is 0.6, right? So I've got that end plate pushing back on it. That's going to be in this direction. That's going to be my radial force R, right, back towards the center. And then I'll have, as this guy rotates, I'll have a force in the transverse direction, theta, given by that. So that's my free body diagram as I go through this. So let's go ahead and write my equation. So I've got some of the forces in the r direction. So again, on this one, I've got my force pushing in the negative r direction, right? Because r is going out from the direction, right? So my r, I don't want to get too messy. I'm not going to draw it on here, but just remember your r axis is out from the center. This is pushing in towards the center, so it'll be negative, and that's going to equal 0.5 AR. That's the mass times the acceleration in the radial direction. Transverse direction, this time this is pushing it in what I'm calling the positive theta direction, so that'll be F theta, and that's going to equal the mass 0.5 times the acceleration in the theta direction. Okay. Then I've got my Z direction, where I've got my normal force pushing up. I've got the weight going down, and that's going to equal the acceleration in the Z mass times the acceleration in the Z direction, which is 0. This thing has no vertical acceleration, right? It's just hanging out where it's hanging out. Okay, so from this one, I can very quickly find that Fz, which is one thing that I want to find, is just going to be 4.9 newtons, which is the weight of the collar. Now, I've got those other ones. I need to find the AR A theta, so I'll go through my R dot, R double dot idea. So R, this thing is sitting at the end there and not moving really, or I should say not radially moving. It's not sliding in and out. It's 0.6 and it is constant at 0.6, right? Because that plate is keeping it in position. So that means R dot is 0, R double dot is 0. Theta, don't really care what theta is. If I do, I'll come back and we'll talk about it. Theta dot is given as 2 radians per second, and it's increasing at 2 radians per second squared. So theta double dot is also 2. Again, that's given in the problem statement right here and here. Okay, so from that I can find that AR is R double dot minus R theta dot squared. Plugging in those values, I get negative 2.4. Do the same thing with theta, which is R theta double dot plus 2R dot theta dot. Plugging in the values that I have there, I get 1.6. So taking these values, plugging them in up here, I get 0.5. AR is negative 2.4. 0.5 times a theta, which is 1.2. And I can find that my radial is 1.2 newtons. And again, those negatives kind of cancel each other. So I'm left with that. And then my transverse force, okay, is 0.6 newtons when I solve for that one. Okay, so again, that radial force of 1.2 newtons is the force that the plate is pushing on the collar. The normal forces, as they talk about there, is that what they call them? Yeah, the normal force. I've got 2 components, right? I've got one going up, right, at 4.9, and then one pushing it, and that's what's making it go around in the circle of 0.6. So those are the forces acting on it. Again, recognizing how it's moving, what information you're given, I can set this up in polar coordinates and more easily find it. It's all setting it up based on what we know about the motion, what we know about the acceleration that makes this problem possible.